Okay, this is a solution to rigid body kinetics number 13. This is the one where you have this butcher knife shaped thing. And it's connected to a hinge at the bottom. So that's what it rotates around. And dimensions. This is 0.3 meters. This is 0.2 meters. And 0.6 and 0.6. And there's a point A here, and we're going to try to calculate the acceleration of that point A. Okay, well, let's just start going through the steps that will always work for any rigid body problem. So first of all, is there a fixed point? Yes. And so the about point is the hinge. So we have to calculate the mass moment of inertia about the hinge. Okay, well, let's figure out the area of this whole thing, and we can start breaking it up into pieces. We'll figure out that, we'll say that the mass of the whole thing is m. Okay, so all we're trying to do now is calculate the moment of inertia about A, but that's a little complicated because this thing just has an unknown mass m. So if I break it up into two pieces, let's say this lower rectangle and this upper rectangle. This one has a mass of 0.3 meters squared. This one has a mass of 0.12 meters squared. And so the whole area is 0.42 meters squared. The area of the top is 0.3 meters squared, and the area of the bottom is 0.12 meters squared. The mass of the whole thing we're calling m. So I'm going to call this, well, I guess I'll keep calling it top and bottom. Okay, so what do we know about the mass of the top? The mass of the top is this much of the total mass. And I'll get that just as a decimal, 0.3 over 0.42. So this is 0.714 m. And the mass of the bottom is 0.12 over 0.42 m. So that's 0.286 m. I guess I could have just subtracted because they have to add up to m. And okay, so now we have to figure out the moments of inertia of each of these about, first we have to figure out the moments of inertia of each of these. Let's see. Okay, well, so we're going to use the formula for a rectangle. So I'm going to figure out the mass moment of inertia of the top rectangle, top rectangle about its center of mass, and then use the parallel axis theorem to calculate the moment of inertia of the top rectangle about the hinge. And then I'm going to do the same thing with the lower one, get its moment of inertia about its center of mass, and then use the parallel axis theorem to calculate the moment of inertia of the bottom rectangle about the hinge. Okay, so the top. So we know that the moment of inertia about that hinge is the moment of inertia about the center of mass plus md, mass of the top, and then the distance from the center of mass of the top to the hinge squared. The formula for the moment of inertia about the center of mass is 1/12 times the mass of the top piece, that's 0.714 m, times 0.5 squared plus 0.6 squared. And then the parallel axis theorem part says 0.714 m times, now what's the distance from the center of mass of the top rectangle to the hinge? Okay, what we're trying to get is, so like, if this is the center of mass of the top rectangle, we want to know the distance from that to the hinge, and squared. So it's going to be, vertically, it's going to be 0.9, and horizontally, it's going to be, let's see, so this is 0.1, so it's going to be 0.15. So I think this is going to be 0.9 squared plus 0.15 squared, and that should do it. And so we get so this first piece is 0.0363 m. The second piece is 0.594 m. So 0.631 m. Okay, that's the moment of inertia about the hinge for the top piece. And then for the bottom piece, it's the same idea. Use the formula for the moment of inertia about the center of mass, and then parallel axis theorem, mass of the bottom times the distance from the center of mass of the bottom to the hinge. So that's 1/12 times the mass of the bottom, 0.286 m, times 0.2 squared plus 0.6 squared, and then the parallel axis theorem part, 0.286 m, times, and the distance from the center of mass of the bottom piece to the hinge is just 0.3 squared. And so the first term, the one just from the formula, is 0.0095 m. And the second piece is 0.0257 m. And add those together and you get 0.035 m. Leave it like that. Okay, so the moment of inertia of the whole thing about the hinge, you can just add those two together. And you get 0.666 m. Okay. So now we have the mass moment of inertia about the hinge. Now we can draw a free body diagram. So you can think of this as the third step. Wherever the centroid of this whole thing is, it's going to be like there somewhere, and there's going to be a weight force acting there that's equal to 9.81 m. We're going to have to calculate where that centroid is. Really, all we need to know is the x coordinate of that centroid, so we could save a couple keystrokes or whatever if we wanted. And then we have a pin joint here that produces some reaction force. That's not going to contribute to the moment. We'll see that that doesn't end up contributing to anything we care about. But okay, let's do the centroid. Well, I'm going to put the origin here. Okay. All right, so the centroid, which is also the center of mass, is equal to 1 over the total area times the sum of the x location of the centroid of each piece times the area of each piece. So first the top piece, so that's 0.3 times the centroid of the top piece. If we're assuming that the origin is at the hinge, that would be 0.15. And then plus the area of the bottom piece. And the location of the centroid, the x coordinate of the centroid is the same as the origin, so that would be 0. And so what we get here for the x centroid, 0.3 times 0.15 divided by 0.42. Whoops, this should have been negative. You know, that's going to be a negative x if the origin is there. And so we come out with an x coordinate of the centroid of negative 0.107 meters. Okay, we can just treat the y coordinate as if it's 0 or something, because you can move the weight force anywhere along its line of action and it doesn't change the problem. But we could have just calculated the x and y centroid coordinates too. And now step 4, we'll set up this table: row, force, moment. And now, well, so first I'll do this force R. That's at the about point. The force is Rx, Ry. The moment is 0. And then we have the weight force. We can treat that like the coordinates are negative 0.1070. And so that's the row vector. That's the vector from the about point to the point where the force is applied. The force is 0, negative 9.81 m. Take the cross product. And you get positive 1.05 m. That's all the forces acting. And now the 5th step is we can think about whether we need Newton's second law or not. Any problem where you have a fixed point, you don't need Newton's second law, at least right now. You might use it later possibly, but so we have a fixed point. And so we'll skip that, and so we'll go to rotational Newton's second law, and we're only doing the z component, everything else is 0. And so what we get for the moments is 1.05 m, and that's equal to the moment of inertia times the angular acceleration. Well, our moment of inertia is 0.666 m. And then multiply that by the angular acceleration. And what you see here is finally, it turns out that the mass doesn't matter at all. These m's cancel out. So whatever that m is, we get the same answer for the angular acceleration. So alpha, the z component of the angular acceleration vector, is 1.577 radians per second squared. All right, well, that was what we wanted. You know, we figured out now this alpha vector is 0, 0, 1.577 radians per second squared. And now we want to figure out the acceleration of the point A. Okay, this point up here in the top left. Okay, it says there's no angular velocity at this instant. So all we have to do now is, you know, the acceleration of the point A is going to come from the watermelon equation. And since there's no angular velocity, this term is going to go away. And so this just comes out to be 0, 0, 1.577 crossed with an r vector. That's the vector that goes from the center of the circular motion to the point. The center of our circular motion is the hinge. And so we just need a vector that goes from the hinge to A. Well, that is negative 0.4 x, 1.2 1.2y. So negative 0.4, 1.2, and we get that that point is accelerating give me a second. Negative 0.4. And you get a final answer of negative 1.89 for the x component, negative 0.63 for the y component, 0 for the z component, meters per second squared. So that's the solution for rigid body kinetics number 13.